Hello everyone, and today's lecture I am going to discuss with you about the how to design the high pass filter. As of now we have discussed about the low pass filter designing, but now this topic is related to the how to design the high pass filter. See, in these questions we don't have any separate designing methods or designing techniques for designing the high pass filter. So that's why to design, if in the examinations, if we are asking about to design the high pass filter, so we have to convert our low pass filter into the high pass filter. That's why we have conversions in the analog domain. So in the conversions in the analog domain concept, we have discussed about how to convert low pass of one cutoff frequency to the low pass to the another cutoff frequency, and low pass to the high pass, and low pass to the band pass and band reject filters. Once again, I am informing you that we don't have any separate designing methods for designing the high pass, band pass and band reject filters. So that's why if such questions are appearing in the examinations, for example like this, design the high pass filter or design the band pass filter or design the band reject filters, so we will take the specifications and we will design the low pass filter first, then we are going to convert that into the high pass filter in appropriate way. Okay, now for proving this concept, I am taking an example. So see this example here. For the given specifications, alpha p is equal to 3 dB, alpha s is equal to 15 dB, omega p is equal to 1000 radians per second, and omega s is equal to 500 radians per second, and design high pass filter. So whatever the specifications he has given for the high pass filter, but we will not design the high pass filter, we will design the low pass filter only. So that after that we will convert that low pass to the high pass. So students, you have to remember this concept. Now, so I am separating the, so as we are designing the low pass filter, so for making the better understanding, I am plotting the two magnitude responses of the high pass filter and the low pass filter. So this is the high pass filter response, and this is the low pass filter response. This is the low pass filter response, but the specifications I have written is here the high pass filter. High pass filter, he has given omega p is equal to 1000 radians per second and omega s is equal to 500 radians per second. So but we are designing the low pass filter, right? So low pass filter, so whatever the pass band in the high pass, in the low pass filter it will be the stop band, right? So to show the difference only, I have plotted here the two magnitudes. This is high pass and this is low pass, right? So whatever the pass band in the high pass will be the stop band in the low pass. Whatever the pass band in the high pass will be the stop band in the low pass. So here the pass band will value will become to the stop band of the low pass filter, and omega s is equal to, now here it become the omega p. So omega p is 1000 here, now omega s is 1000 here, omega s is 500 here, and omega p is 500 radians per second here. This is the first point you should be keep in mind. So I am taking the attenuations as it is. Alpha s is equal to 15 dB and alpha p is equal to 3 dB. Now forget about the high pass filter. You have low pass filter, omega s, omega p, and alpha s and alpha p. Now we will design the high pass filter. Here he did not asking you to use the particular method. So we have two types of methods of the analog filter designing. One is Butterworth filter and second one is the Chebyshev filter. He didn't specify which method we have to follow, but so that's why compared to the Butterworth filter and Chebyshev filter, Butterworth filter is having the flag magnitude response. That's why we are going for the Butterworth filter designing only, and moreover designing also very easy compared to the Chebyshev filter, because in the Butterworth filter we will obtain the transfer function without deriving the poles. Okay, so that's why I am going for the Butterworth filter designing. Now according to the Butterworth filter designing, the formula for calculating the order n is equal to logarithm of 10 power 10 into 0.1 into alpha s minus 1 by 10 power 0.1 into alpha p minus 1 whole divided by log of omega s minus omega p. This is the fixed formula for calculating the order n in the Butterworth filter. So I have substituted the values which have given. So 0.1 into alpha is 15 dB, 15 dB I have substituted here, minus 1 by 10 power 0.1 into alpha p is equal to 3 dB. 3 dB I have substituted here, minus 1 whole divided by log of omega s is equal to 1000 and omega is equal to 500. So after doing the mathematical calculation using the calculators, I got this value, n is equal to 2.468. So now rounding off it to the next integer value, I got n is equal to 3. So the order is equal to 3 I got. So for the order is equal to 3, the Butterworth polynomial for the denominator function is equal to 1 by s plus 1 into s square plus s plus 1. So this I have given you the fixed Butterworth polynomials for the normalized filter. So I have taken this. Now whatever the transfer function we got here is the transfer function of the low pass filter, but actually in the problem he is asking you to design the high pass filter. So it means that you have to convert this low pass filter transfer function into the high pass filter. So for doing that, so you have to substitute the value of s. In place of s, you have to substitute omega c by s. Omega c is the cutoff frequency. Omega c is the cutoff frequency. So we don't have any value to the cutoff frequency has been given, but we know the omega c is equal to omega p of the filter. But here omega p is equal to 1000 radians per second, because here I am taking the high pass value only. Omega c is equal to omega p is equal to 1000 radians per second. So omega p is equal to 1000 radians per second. Here you have to take 1000. So you may ask you, why madam, why we are taking 1000 radians per second, but previously we have taken omega p is equal to 500. Yes, we have taken the omega p is equal to 500 in the low pass design. Now this is the time for converting the low pass into the high pass. So in the high pass, the omega p is equal to 1000 radians per second. That's why we have taken 1000 radians per second. So in place of this in place of this low pass filter transfer function, substitute in place of s, substitute 1000 by s, you will get the high pass transfer function. Now see this, h of s is equal to, so here s plus 1, right? So 1000 by s plus 1 into s square, 1000 by s whole square, plus s is equal to 1000 by s plus 1. So after doing the simplifications, I got the transfer function is equal to, say here I am taking the LCM and all. Okay, 1000 by s plus 1 LCM I have taken. So this is also I am expanding 1000 whole square by s square plus 1000 by s plus 1. After multiplying this, you got, if you go this denominator into the numerator, s cube by s plus 1000 into s square plus 1000 s plus 1000 whole square. So this is the final transfer function of the high pass filter. It means that I can say that if you got the transfer function, it means that you have designed the filter. Okay, see you. Please subscribe my channel.